Ancient artisans achieved material science breakthroughs that still baffle modern engineers. This journey uncovers 25 secrets behind their impossible creations, from Roman concrete that repairs itself to Damascus steel with a hidden nanostructure. By the end, you will fundamentally change how you view human history and technological progress. How did they create glass that changes color with just a flick of the wrist, or forge iron that never rusts after 1600 years? What does our most advanced science miss that their hands-on genius understood? How much of our own knowledge might one day be forgotten just as theirs was? Their genius was born not from formulas but from fire. For millennia, these master craftsmen engaged in a silent, painstaking dialogue with the natural world. They learned to read the subtle colors of a flame to gauge a furnace temperature, or to judge the quality of an ore by the way it fractured under a hammer. This was a science of the senses, a deep material wisdom passed from one generation to the next through the sacred bond of apprenticeship. A young person would spend years, sometimes decades, beside a master, not just learning recipes, but absorbing an entire philosophy of making. They learned which clay deposits were best after the autumn rains, or how a specific type of wood ash could transform ordinary sand into a brilliant, clear glass. This knowledge was their most precious inheritance, guarded as closely as any state secret. It was a living library, written in the movements of skilled hands and the intuitive understanding of how materials behave under stress, heat, and time. The Mesopotamian bronze caster did not know the atomic theory of copper and tin, but he knew precisely how long to work the molten metal to achieve a blade that would not shatter. The Alexandrian glassblower could not define light refraction, but she could create a mosaic glass vessel with colors so vibrant they seemed to capture light itself. They were manipulating the very building blocks of matter, achieving nanostructures and complex chemical reactions long before those words had any meaning. Their laboratory was the workshop, their instruments were their own sharpened perceptions, and their results stand today as a quiet challenge to our own technological arrogance. This foundational mastery raises a profound question. If they could achieve so much with so little, what crucial element of that hands-on wisdom have we forgotten in our age of perfect digital models and synthetic materials? That silent dialogue with the natural world yielded its first incredible secret in the very foundations of an empire. Roman engineers created a marine concrete that does something modern science still struggles to replicate. It heals itself. While our own concrete harbors and seawalls crumble into the saltwater after just 50 years, Roman piers stand defiant after 2000. The difference is not just in their recipe, but in their philosophy. Modern Portland cement fights a losing battle against seawater, which slowly erodes and weakens its structure. The Romans, in their brilliance, designed a material that would form an alliance with the ocean itself. Their concrete was a mix of lime and volcanic ash, specifically a type of ash from the Italian town of Pozzuoli. When this special blend was submerged, something magical began to happen. Seawater filtering through the cracks that inevitably form would not cause damage. Instead, it triggered a slow, continuous chemical reaction. The water interacting with the lime and volcanic ash would grow rare, plate-like crystals of a mineral called aluminous tobamorite. Think of these crystals as microscopic repair crews. Whenever a new crack appears, seawater seeps in, and the chemical process kicks in again, growing more crystals that fill the gap and lock it shut. The concrete does not just resist the sea, it uses the sea to become stronger, harder, and more resilient with every passing century. Researchers at the University of Utah only confirmed this self-healing mechanism in recent years, solving a mystery that has baffled engineers for generations. This ancient principle holds the key to our future, offering a blueprint for building coastal cities and infrastructure that can withstand rising seas and intensifying storms. It is a stunning reminder that sometimes the most advanced solution is not to fight nature, but to work with it. While Roman concrete found strength in its alliance with nature, another ancient secret was forged in the heart of the fire itself. The legendary swords of Damascus possessed a cutting edge that has never been truly duplicated. These were not merely sharp blades, they were living, breathing material, famous for their beautiful, watery surface pattern and their almost supernatural performance. A Damascus blade was said to be so flexible it could bend from hilt to tip and spring back perfectly straight, and so sharp it could cleave a silk scarf drifting in the air. For centuries, the secret of this steel was lost to history, a ghost in the forge. The answer, it turns out, was written in a language so small no ancient smith could ever have read it. Modern scientists, using powerful electron microscopes, finally peered into the soul of the metal. What they discovered was breathtaking. The steel contained carbon nanotubes and incredibly hard cementite nanowires, structures so advanced we consider them modern nanotechnology. These were not accidental impurities. They were the deliberate product of a lost art. The process began with a special type of high-carbon steel from India known as woots. Master smiths would take this raw ingot and subject it to a meticulously controlled ritual of heating and hammering. They were not just shaping the metal, they were orchestrating the arrangement of carbon atoms within it. Through specific thermal cycling, they encouraged the carbon to precipitate out of the iron solution, forming those super-strong nanowires. The repeated folding and forging then aligned these nanostructures into the laminations that create the blade's iconic swirling pattern. Each curve in that beautiful watering is a fossilized record of a nanoscale event, a testament to a craftsman's intuitive control over matter. The tragedy is that the full, precise sequence of temperatures, hammer blows, and cooling rates died with the last masters. Today, our most advanced metallurgists, with all their digital furnaces and scientific instruments, are still trying to reverse engineer the exact conditions needed to recreate these self-assembling nanostructures consistently. We can see the result of their genius under the microscope, but we have lost the hands-on wisdom that made it possible. From the forge's intense heat, we travel to the humid jungles of the Maya, where another secret was born not from metal but from color. A single, vibrant blue pigment has defied 15 centuries of tropical sun and torrential rain, refusing to fade where every modern synthetic color would have long since washed away. This is Maya blue, and its resilience is a masterpiece of molecular architecture. The Maya did not simply mix a dye with clay. They performed what seemed like a sacred alchemy, heating a specific palygorskite clay with indigo dye and the sacred copal incense in a precise ritual. This was not mere superstition, it was a sophisticated chemical recipe disguised as ceremony. The heat opened up the microscopic tunnels within the clay's crystal structure. The indigo molecules, carried by the smoke and vapors, would then travel into these tiny channels and become permanently trapped. Once inside, they were locked in place, shielded from the destructive energy of ultraviolet light and the corrosive effects of water. The result was a hybrid material, a pigment where the organic dye and the inorganic clay became one stable entity. Think of it as a supremely durable apartment building built for color molecules. The clay structure is the strong, earthquake-proof building, and the indigo molecules are the residents safely locked inside, protected from the harsh weather outside. Modern science has only recently decoded this process, yet even with our advanced labs, we cannot perfectly replicate the color's legendary stability. Our best industrial pigments still bleach and weaken under the same conditions. The Maya secret was a perfect storm of the right clay, the right dye, and a precisely controlled thermal process they perfected through generations of observation. This ancient blue offers a profound lesson for our own future, showing us how to design new materials, from durable outdoor paints to advanced medical coatings, that can stand the test of time by protecting their active components at the most fundamental level. The same intuitive genius that created self-healing concrete and nanostructured steel appeared in the foundries of ancient China. Shang Dynasty bronze casters were not merely making objects, they were engineering materials at a molecular level, tailoring the very soul of the metal to its intended purpose. They understood that a ritual vessel, a battle axe, and a set of bells could not be made from the same substance. Through painstaking experimentation, they perfected a system of alloy composition that varied dramatically. A ceremonial food vessel meant to withstand centuries of gentle handling would be cast with a specific ratio of copper, tin, and lead, creating a beautiful, corrosion-resistant piece. But a sword or an arrowhead required a completely different recipe, one that prioritized hardness and tensile strength to hold a deadly edge. They even composed specific alloys for musical instruments, blending metals to achieve perfect, resonant tones that have lasted for 3,000 years. This was not guesswork. Modern metallurgical analysis of these artifacts reveals that the ancient smiths were intentionally creating different crystalline structures within the bronze by controlling how quickly it cooled. A slow, controlled cooling process would yield a softer, more ductile metal, ideal for intricate vessels. A rapid quench would create a harder, more brittle structure, perfect for a weapon's cutting surface. This mastery is stunningly embodied in the Humawu Ding, a colossal ritual cauldron weighing over 875 kilograms. Casting such a monumental piece was a breathtaking feat of engineering. It required the creation of numerous sectional clay molds, assembled with perfect precision. The pouring of the molten bronze had to be a continuous, synchronized operation, and the cooling process meticulously managed over days to prevent catastrophic thermal stresses from cracking the giant vessel. This was not just art, it was a systematic, scientific approach to alloy design that predates our modern discipline of materials science by millennia. They were manipulating the phase diagrams of copper and tin alloys, controlling crystal growth, and optimizing for properties like hardness and acoustic resonance, all without a single written formula. Their laboratory was the foundry floor, their textbook was the accumulated wisdom of generations, and their legacy is a collection of artifacts that continue to reveal new depths of their understanding. Far out in the North Atlantic, under a sky choked with iron-gray clouds, a Viking longship held its course. With no visible sun or stars for days, such a journey should have been impossible, a voyage into pure guesswork. Yet Norse sagas speak of a magical stone, the Solarstein, that could reveal the hidden sun. For centuries, this was dismissed as mere legend. We now know it was not magic, but a breathtaking application of optical physics. The Vikings were using crystals of a transparent calcite mineral, known today as Icelandic spar, to see the unseen. This crystal possesses a unique property called birefringence. It splits a beam of light into two separate paths. When you hold such a crystal up to the sky and look through it, even on a completely overcast day, you are not just seeing uniform grayness. The crystal reveals patterns of light and dark, a subtle interplay of brightness that shifts as you rotate the stone. The key is polarized light. Sunlight becomes polarized as it scatters through the Earth's atmosphere, meaning its light waves vibrate in a specific direction. The cloud cover diffuses this light, making the polarization pattern invisible to our naked eyes. But the calcite crystal acts as a filter. By rotating it and looking for the point where the two images seen through the crystal match in brightness, a skilled navigator could pinpoint the exact position of the sun, even when it was fully obscured behind the clouds. The proof emerged from a shipwreck off the British island of Alderney, where a piece of Icelandic spar was found alongside navigational tools dated to the 16th century. Laboratory experiments confirmed the method's stunning accuracy, allowing navigators to locate the sun with a precision of within a single degree. This was not a vague directional aid. It was a precise celestial instrument carved by nature and understood by human genius. The Vikings possessed a working knowledge of light polarization 1,000 years before the scientific principle was formally defined by physicists. Today, researchers are looking back to this ancient secret to develop robust backup navigation systems for aircraft and ships, systems that cannot be jammed or disrupted like modern GPS. It is a profound testament to the power of observing the natural world with absolute clarity. They did not need to understand the theory of wave optics. They only needed to hold the crystal to the sky and know how to read the story it told. An object can possess its own secret recipe for beauty. Deep within the workshops of ancient Egypt, artisans perfected a ceramic so unique it seemed to create its own shimmering skin. This was faience, a material that glazed itself from the inside out, a brilliant blue-green beacon of rebirth crafted from the most humble of ingredients. They achieved this miracle not with a brush or a separate glazed pot, but through a profound understanding of chemistry in motion. The recipe was deceptively simple: crushed quartz sand, a small amount of clay, alkaline salts harvested from the desert, and mineral colorants like copper to produce that iconic turquoise hue. The magic, however, was in the process. After the paste was shaped into a scarab or an amulet, it was left to dry. As the water within the mixture began its slow journey to the surface through evaporation, it did not travel alone. It carried the dissolved alkaline salts with it, drawing them outward to coat the entire object in a crystalline film. When the dry object was placed into the kiln, the heat worked its final transformation. Those migrated salts on the surface melted into a hard, glossy, glassy coating, a perfect glaze that was born from the body of the object itself. This technique, known as efflorescence, meant the glaze was not a separate layer applied on top. It was an integral part of the material, fused to the core in a single firing. The Egyptian craftsman was not just a potter, he was a director of molecular traffic, guiding salts and water on a predetermined path to achieve a stunning visual effect. Today, this ancient secret offers a powerful model for sustainability. Modern glazes often involve toxic heavy metals and require a second, energy-intensive firing process to apply them. The self-glazing mechanism of faience points toward a future of cleaner ceramic production, where materials are designed to finish themselves, eliminating waste and hazardous compounds. It is a timeless lesson in efficiency, showing us that the most elegant solution often lies not in adding more, but in cleverly orchestrating what is already there. While the Vikings read the sky with crystals, the Byzantine Empire mastered a more terrifying form of elemental control, one that turned the very sea into a sheet of fire. Greek fire was the ancient world's ultimate naval weapon, a liquid flame that could not be extinguished with water, a horror that clung to ships and men, burning even as they sank beneath the waves. Historical accounts describe a sticky, fiery stream projected from bronze tubes mounted on the prows of their warships, a continuous jet that sowed panic and ensured naval dominance for centuries. The secret was so closely guarded that its exact composition died with the empire, but modern forensic science has pieced together a plausible and brilliant recipe. The base was almost certainly a form of distilled petroleum, similar to modern naphtha, but the true genius was in the additives. The Byzantines likely incorporated substances that underwent a pyrophoric reaction, meaning they ignited spontaneously upon contact with water. Think of throwing a scoop of water onto a grease fire. The result is a dangerous splatter. Now imagine a substance designed to do the exact opposite, to use that splash of water as its own ignition source and fuel. Recent experiments point to components like quicklime, which generates intense heat when it meets water, or even calcium phosphide, which releases phosphine gas that bursts into flame on contact with the air. This would create a terrifying feedback loop where sailors trying to douse the flames with buckets of seawater would only feed the inferno, making it burn hotter and more fiercely. The delivery system was a marvel in itself, a complex apparatus of pressurized tanks, pumps, and heated siphons that allowed the mixture to be projected as a continuous, roaring stream rather than a simple lobbed pot. This was not just a weapon, it was a sophisticated chemical delivery system, an early mastery of combustion physics and fluid dynamics. The operators were not mere soldiers, they were the first chemical engineers, understanding the precise ratios and pressures needed to turn a secret brew into an unstoppable force. We have since rediscovered the principles behind such incendiaries, but the original, perfected formula of Greek fire remains one of history's most powerful and enduring secrets, a stark reminder of the destructive potential of ancient material science. The same intuitive genius that mastered fire and chemical reactions also thrived in a world without it. Far from the blazing forges of other ancient cultures, the indigenous peoples of North America's Great Lakes region developed a metalworking tradition that defied conventional wisdom. They worked with pure, elemental copper found in its natural metallic state, and they shaped it not by melting but by the force of their hands. This was a science of cold hammering, a patient, percussive dialogue with one of nature's purest metals. Their craft began with a profound geological knowledge, an ability to identify surface deposits of native copper that were 99% pure, but pure copper is notoriously difficult to work. Hammer it too much and it becomes brittle, hardening until it cracks and shatters. These master artisans discovered a crucial secret, the process of annealing. They learned that by periodically heating the copper in a controlled fire to a specific, dull red heat, they could relieve the internal stresses. They were not melting the metal, but gently persuading its crystalline structure to relax and become malleable again. This cycle of hammering and annealing allowed them to create intricate tools, lethal spear points, and beautiful ornaments, all from a single, unalloyed piece of earth. Modern analysis reveals the sheer brilliance of their method. This careful working and heating produced an optimal grain structure within the metal, a fine, interlocked crystalline arrangement that gave their artifacts a perfect balance. The tools were hard enough to hold a sharp edge, yet tough enough to absorb impact without fracturing. Furthermore, because they used pure copper without smelting, their artifacts were free from the arsenic, lead, and other impurities that often made smelted copper from other parts of the world brittle and prone to corrosion. This is why pieces recovered from the earth after thousands of years are often found in a state of pristine preservation, their metallic luster still visible. They achieved a material perfection that our own industrial processes, with their complex alloys and energy-intensive smelting, often struggle to match. This ancient cold working tradition stands as a powerful testament to a different path in technological evolution, one that sought harmony with materials rather than domination over them. It proves that the highest forms of material science can be born from patience, observation, and a deep, respectful connection to the resources at hand. The Japanese katana is a paradox of steel, a blade that is at once lethally sharp and astonishingly resilient. Its legendary status was not born from a single magical ingredient, but from a master swordsmith's profound understanding of material architecture. The secret lies in the soul of the folding process, a ritual that transforms a block of heterogeneous steel into a perfectly balanced composite material. The smith begins with two different types of steel, a high-carbon outer jacket and a softer, lower-carbon core. Through a meticulous process of heating, hammering, and folding, sometimes over a dozen times, the smith does not simply mix these metals. He is creating a laminate of thousands, even tens of thousands, of microscopic layers, each with a slightly different carbon concentration. This intricate internal structure solves two critical problems at once. It evenly distributes any harmful impurities or slag inclusions that were present in the raw Tamahagane steel, preventing a single weak point from causing a catastrophic failure. More importantly, it builds a blade with a gradient of properties. The hard, high-carbon steel that forms the razor-sharp edge can be honed to an almost molecular thinness. Yet, if this brittle steel comprised the entire blade, it would shatter upon impact like glass. The softer, more ductile core steel acts as a shock absorber, flexing to dissipate the energy of a blow and preventing the blade from breaking. This is the genius of the katana. It is hard where it needs to cut and soft where it needs to bend. The final act of genius is the clay tempering. Before the final heat treatment, the smith paints the blade with a special clay slurry, applying a thinner layer along the cutting edge and a thicker one along the spine. When the glowing hot blade is quenched in water, the thinly coated edge cools almost instantly, transforming its crystalline structure into an incredibly hard, needle-like formation called martensite. The spine, insulated by the thick clay, cools slowly, retaining a softer, more flexible perlitic structure. The visible line between these two zones is the hamon, that beautiful, wavy pattern that is the blade's unique fingerprint. This is not mere decoration. It is a direct map of the controlled thermal gradient that gives the katana its soul. The hard martensitic edge holds its sharpness through brutal use, while the softer spine and core grant it a life-saving flexibility. Today, our most advanced composite materials, from the layered ceramics in bulletproof vests to the carbon fiber in aircraft wings, operate on this very same principle, combining materials with conflicting properties to create a new whole that is greater than the sum of its parts. Yet we achieve this through immense industrial effort, with autoclaves and presses consuming vast amounts of energy. The swordsmith achieved a similar, and in some way superior, result with nothing but fire, hammer, water, and an intuitive mastery of steel's inner world. Even the most brutal desert heat was no match for the ingenuity of ancient Persian architects. They mastered the art of creating cool comfort from thin air, building structures that functioned as completely passive air conditioning systems. These were the wind catchers or badgers, elegant towers that rose above the skyline of cities like Yazd, not for decoration, but as sophisticated thermodynamic machines. Their operation was a quiet symphony of physics. By capturing the faster, cooler breezes that travel high above the ground, the wind catcher funneled this air down a vertical shaft and directly into the heart of a building. But the genius did not stop there. Often, this incoming air would be directed to pass over an internal pool of water or a kanat, which is an underground canal. This introduced the powerful effect of evaporative cooling. As the dry desert air moved over the water's surface, it caused the water to evaporate, a process that absorbs heat energy from the surrounding air, chilling it dramatically before it flowed into the living spaces. The design was even more clever. Many wind catchers had multiple openings oriented to catch winds from any direction. More importantly, the system created a natural convection cycle. As hot, stale air inside the building rose, it would be drawn out through a separate shaft, creating a continuous, self-sustaining flow of ventilation without a single moving part. This was not just a simple breeze catcher, it was a precise manipulation of pressure differentials and fluid dynamics. The architects even integrated the stable, cool temperature of the Earth itself by connecting some systems to underground canal tunnels, using the ground as a massive heat sink. Today, as we grapple with the enormous energy demands of modern air conditioning, engineers are looking back to these ancient solutions. The principles of the badger are being studied and incorporated into contemporary sustainable design, offering a blueprint for cooling buildings in our hottest climates without consuming a single watt of electricity. This ancient secret challenges a core assumption of modern life, that comfort requires complex, energy-hungry machinery. It proves that the most elegant solutions often work in harmony with the fundamental laws of nature, not against them. High in the Andes, the stones themselves learned to dance. The Inca stonemasons who built Machu Picchu and the Coricancha temple faced a constant, terrifying reality: the violent earthquakes that shake the mountains to their core. Their solution was not to build stronger, but to build smarter, creating structures that moved with the earth instead of fighting against it. They perfected a style of polygonal masonry, carving massive granite blocks into complex, irregular shapes that fit together like a three-dimensional jigsaw puzzle of incredible complexity. The legendary precision is true. You cannot slide a knife blade between these stones. But this tight fit was only the beginning of their genius. The walls were built with a slight inward incline, and the stones themselves were often slightly convex on their outer faces. This was not for aesthetics, it was a profound understanding of structural dynamics. When an earthquake strikes, the energy needs somewhere to go. In a rigid, mortared wall, that energy has no escape, and the structure shakes itself apart. In an Inca wall, the interlocking stones have just enough freedom to move. The seismic waves make the entire structure sway, and the individual stones shift and rotate against one another in a carefully choreographed performance. They literally dance in their sockets, the energy of the quake being dissipated as friction between the countless stone faces. When the shaking stops, gravity and the perfect fit of the blocks pull them seamlessly back into their original positions. It is a self-stabilizing system of breathtaking elegance. The proof stands in Cusco at the Coricancha temple. The flawless Inca stonework at its base has survived every major earthquake for centuries. Sitting directly on top of it are the ruins of a Spanish church, built from the same stone but using conventional mortar and rigid rectangular blocks. Time and again, the Spanish sections have crumbled into rubble while the Inca foundations remained unshaken. Modern seismic engineers now study these ancient walls, recognizing them as a masterclass in base isolation and energy dissipation. We are only now relearning this principle for our own skyscrapers, using complex systems of rubber bearings and pendulums to allow buildings to sway safely. The Inca masons achieved the same result by listening to the land and understanding that true strength lies not in rigid resistance, but in intelligent, graceful movement. Roman glassmakers held the power to trap light itself within their creations. A humble drinking cup, the Lycurgus cup, reveals this secret in a breathtaking display. Seen in ordinary reflected light, it glows a deep, jewel-like green, but hold it up to a light source and look through it, and the glass transforms, transmitting a stunning, rich ruby red. This is not a trick of the eye, it is a deliberate manipulation of light at the smallest possible scale. For centuries, no one could explain how this ancient magic was achieved. The answer was finally revealed under the gaze of a modern electron microscope. Suspended within the glass matrix are nanoparticles of gold and silver, each 1,000 of times smaller than a grain of pollen. The Roman artisans, through a process lost to time, had somehow infused the glass with these precious metals in just the right proportions, and then controlled the heating and cooling cycles with absolute precision. This process, known as striking, caused the metals to precipitate out of the molten glass as these infinitesimally small colloids. The color shift, the dichroic effect, is a result of how these tiny metal particles interact with light. They scatter some wavelengths and allow others to pass through, depending on the angle of the light and the position of the viewer. The green you see in reflected light is the scattered light, while the red you see in transmitted light is the light that passes directly through the nanoparticle filter. This was not just beautiful artistry, it was a conscious application of nanotechnology, a manipulation of matter at the scale of individual atoms, 1,600 years before the term was even invented. Today, we use these very same principles to create advanced optical filters and sensors for spacecraft, materials that must respond with absolute precision to different wavelengths of light. Yet we achieve this with million-dollar vacuum chambers and ion beams. The Romans did it with a clay crucible, a wood fire, and an artisan's intuitive genius for timing and temperature. This ancient cup stands as a quiet challenge, forcing us to wonder how many other material secrets were born from that profound, hands-on dialogue between human creativity and the hidden potential of matter. That same intuitive control over fire and earth reached its ultimate expression in the kilns of ancient China. While Roman glass manipulated light and Damascus steel forged nanostructures, Chinese potters pursued a different kind of perfection, a material that was both ethereally delicate and impossibly strong. Their quest gave the world true porcelain, a substance so coveted it was valued on par with gold. The secret was not a single ingredient, but a symphony of geology, chemistry, and thermal mastery. At its heart was a unique white clay known as kaolin, a material that remains the global standard for fine porcelain to this day. Kaolin's magic is its purity and its high fusion point. While common clays would melt into a puddle at extreme temperatures, kaolin holds its shape, undergoing a profound internal transformation called vitrification. The Chinese potters learned to guide this transformation with breathtaking precision. They understood that the kiln's atmosphere was as important as its heat. A clean, oxidizing fire was essential to burn away any residual organic impurities, ensuring the final piece would be a brilliant, flawless white. But the true genius was in the temperature profile, a carefully choreographed thermal dance that might last for days. The kiln had to be raised to a searing temperature, often exceeding 1,300 degrees Celsius, hot enough to make the kaolin particles begin to fuse into a dense, glass-like network. Yet this intense heat had to be applied evenly and held for just the right amount of time. A moment too short and the body would remain porous and weak. A moment too long or a slight hot spot in the kiln and the entire piece would slump and warp, its beauty collapsing into a melted ruin. To this base of kaolin they added a crucial partner, a feldspathic rock called petunci or China stone. When fired, the petunci melted into a glassy phase that flowed between the more stable kaolin particles, binding them together in a strong, translucent matrix. This is what gives a fine porcelain cup its characteristic ring when tapped, a clear, bell-like tone that signals its complete vitrification and internal integrity. For centuries, European alchemists and potters tried desperately to crack this code, examining shards of imported porcelain as if they were fragments of another world. They experimented with countless local clays and recipes, but their attempts always resulted in opaque, heavy earthenware or soft paste porcelain that lacked the strength and brilliance of the true Chinese material. It was not until the early 18th century, after the discovery of rich kaolin deposits in Germany, that Europeans finally replicated the process, a technological achievement that sparked its own industrial revolution. The principles these ancient Chinese masters perfected are the very foundation of modern advanced ceramics, materials used in everything from the heat shielding on spacecraft to the biocompatible implants in our own bodies. We now have digital kilns that control every degree with microchip precision, yet we are still following the fundamental recipe they established through centuries of silent, painstaking observation. Their legacy is a testament to the power of understanding not just what a material is, but what it can become under the perfect application of heat and time. Long before the invention of the glassblower's pipe, artisans in Mesopotamia were already performing miracles with molten silica. They invented a technique known as core forming, a complex and delicate dance of materials that produced some of the world's earliest intricate glass vessels. The process began not with glass but with a core of clay and dung meticulously shaped around a metal rod. This humble core was the hidden heart of the masterpiece to come. The artisan would then heat rods of raw glass until they were soft and pliable, carefully winding them around the clay form, building up the body of the vessel layer by layer. This alone required a deep, intuitive feel for the material, but the true test of their skill came with the decoration. They would apply delicate threads of colored glass, creating intricate patterns while the vessel was still hot and semi-solid. This demanded a flawless understanding of thermal properties. The colored glass threads had to be applied at the exact moment when they were molten enough to adhere, but the base vessel body had to be just cool enough to not slump out of shape from the additional heat. They were intuitively navigating the glass's viscosity, a property that changes dramatically with every few degrees of temperature change. The final and perhaps most precarious stage was the cooling. The glass, the clay core, and the metal rod all expand and contract at different rates when heated and cooled. If the cooling was too rapid or uneven, the differential stress would instantly shatter the glass into 1,000 pieces. These ancient masters had to empirically discover the perfect, slow cooling rate that would allow each material to contract at its own pace without fighting the others, a brilliant, unspoken mastery of thermal expansion coefficients. Once the object was completely cool, the final act of revelation occurred. They would meticulously scrape out the fragile clay core through the vessel's narrow neck, leaving behind a hollow, brilliantly decorated glass bottle. This was a technology of profound patience and precision, a secret art that laid the entire foundation for the glassblowing revolution that would later sweep through the Roman and Islamic worlds. It stands as a powerful reminder that the most elegant technologies are not always about speed, but about the deep, patient understanding of how materials live and breathe with heat. Standing in the heart of Delhi for 16 centuries, a 7-ton iron pillar has defied the very essence of decay. While modern steel structures require constant painting and maintenance to fight off rust, this ancient monument has endured monsoon after monsoon, its surface bearing only a thin, stable patina. For generations, this seemed like a miracle, a defiance of the natural laws that govern metal. The secret, however, was not in the pillar's defiance of chemistry, but in its perfect collaboration with it. Modern metallurgists, armed with scanning electron microscopes and X-ray diffraction, finally decoded its immunity. They discovered that the pillar is protected by a film so thin it is almost invisible, a layer of a rare compound called mesowite. This is not a coating applied to the metal, but a skin that grew from the metal itself, a perfect barrier of iron, oxygen, and hydrogen that shields the pillar from further attack by moisture and air. The creation of this protective skin was a happy accident of ancient craftsmanship, the iron used by the smiths came from a unique source, one that was unusually rich in phosphorus. During the forging process, where modern iron is worked at high heat to remove impurities, the Indian smiths used a different technique. They hammered the iron at a lower temperature, a method that inadvertently preserved the high phosphorus content within the metal matrix. As the pillar aged over its first few years, this phosphorus reacted with the atmosphere, catalyzing the slow, steady formation of that continuous mesowite layer. It acts exactly like the chromium oxide layer that protects modern stainless steel, a self-renewing shield that prevents oxygen from reaching the pure metal beneath. The ancient ironworkers did not know they were creating a passive protection layer, a concept that would not be formally understood for another 1500 years. They were simply using the best materials and techniques available to them, and in doing so, they engineered a form of rust that fights rust. This pillar stands as a monumental lesson in the wisdom of impurity. In our drive for 100% pure materials, we often strip away the very elements that, in the right combination and with the right process, can provide the most elegant and durable solutions of all. Buried in a shipwreck for 2,000 years, a corroded lump of bronze and wood held a secret that would shatter our understanding of ancient technology. When archaeologists first recovered the Antikythera mechanism, they assumed it was a simple navigational instrument, but decades of painstaking analysis using X-ray tomography and high-resolution imaging revealed the truth. This was an analog computer of breathtaking complexity, a device that could predict the movement of the heavens with a precision that would not be matched for over a millennium. At its heart were dozens of interlocking bronze gears, each one meticulously hand-cut with triangular teeth. The genius of the device was not just in its existence, but in the mathematical poetry etched into every wheel. The tooth counts were not arbitrary. A gear with 64 teeth might mesh with one of 38, a ratio specifically designed to model the subtle wobble in the moon's orbit, a phenomenon known as epicyclic motion. This was not a simple calendar, it was a dynamic simulation of the cosmos, built from bronze and intellect. The most stunning revelation was the presence of a differential gear, a complex assembly that allows two different rotational speeds to be combined into a single output. This technology was thought to have been invented in the 16th century for use in sophisticated clocks and later the axles of modern automobiles. Yet here it was in a device crafted around 80 BC, calculating the ever-changing phases of the moon. The metal itself was a secret, a specialized bronze alloy formulated not just for strength but for a low coefficient of friction. This allowed the tiny gears, some no larger than a coin, to mesh and turn smoothly against each other for decades without seizing or wearing down. Just imagine the mind that conceived this. A single artisan or a small school of philosophers, working without blueprints or precision lathes, who understood orbital mechanics so deeply they could translate the dance of the planets into a symphony of interlocking bronze. Each turn of the hand crank was a step forward in time, moving celestial indicators across dials that showed the positions of the sun, moon, and known planets, even predicting eclipses. This was not magic or superstition. It was a working model of the universe built on a foundation of advanced mathematics, metallurgy, and mechanical engineering that we never believed the ancient world possessed. The Antikythera mechanism stands as a solitary, profound question mark in the archaeological record. It forces us to wonder how much knowledge was lost in the fires of burning libraries, or simply faded away when the last keeper of a secret took it to the grave. A seemingly simple basket could hold water as reliably as a clay pot or a leather pouch. This was the everyday genius of indigenous artisans across North America, who engineered natural materials into perfectly watertight containers without a single drop of glue or sealant. The Pomo people of California, for instance, mastered a specific technique using the roots of the sedge plant. They wove these roots in a pattern that was deliberately tight, but with an innate intelligence. When the basket was dry, it was a sturdy vessel, but when water was added, the plant fibers absorbed the moisture and began to swell. This was not a flaw, it was the very purpose of the design. The swelling acted like a million tiny fingers, tightening the weave and closing any microscopic gaps, creating a seal that grew more perfect the longer it held liquid. Other tribes, like the Tlingit of the Pacific Northwest, selected split spruce roots for their work. These roots contained their own hidden ingredient, natural resins and waxes that acted as a built-in water repellent. The weaving pattern itself was a lesson in fluid dynamics. A skilled weaver could create a spiral structure that naturally channeled water away from the seams and openings, while the overall flexibility of the construction allowed the basket to withstand bumps and drops without cracking, a quality rigid pottery could never match. This was not merely craft, it was a profound application of biomimicry and structural engineering. The artisans were using geometry as a tool for waterproofing, creating a functional seal through the intelligent arrangement of fibers rather than the application of a chemical layer. Today, material scientists look to these ancient baskets for inspiration in designing sustainable packaging. Imagine a cardboard box that, upon contact with moisture, tightens its own structure to protect its contents, or a food container that uses a specific woven pattern to repel liquids without any plastic lining. These indigenous secrets offer a powerful alternative to our current reliance on synthetic sealants and coatings, pointing toward a future where protection is woven into the very architecture of an object, not just painted on the surface. The same meticulous control over natural chemistry that gave us self-glazing faience was applied to an even more delicate medium, the very surface of recorded thought. Ancient Egyptian papyrus makers engineered a writing material of such elegance and durability that it has preserved the voices of the past for over 5,000 years. Their process was a quiet alchemy, transforming the humble stalks of the cypress papyrus plant into a flexible, resilient sheet. They began by slicing the pith of the plant into thin, vertical strips. These strips were then laid side by side, forming a single layer. A second layer of strips was placed directly on top, but this time running horizontally. This simple crisscross pattern was the beginning of a profound molecular transformation. The true genius was in the next step, the hammering. They did not merely press the layers together, they pounded them with a precise, rhythmic force. This physical action was the catalyst. The hammering broke down the plant's rigid cellular walls, rupturing the tiny vessels that ran along the stalks. From within these broken cells, a natural sap was released, a sticky substance rich in polysaccharides. These long-chain sugar molecules are nature's own glue. As the layers were pressed and left to dry under heavy weights, this liberated sap seeped between every fiber, bonding the vertical and horizontal strips not just mechanically but chemically. The polysaccharides formed a molecular web, creating a single, unified sheet from two distinct layers. The result was a material with a perfect balance of properties. It was flexible enough to be rolled and unrolled countless times without cracking, yet strong enough to resist tearing. Its surface was smooth and absorbent, ideal for ink, but the internal bonding made it resistant to moisture and decay. Modern paper made from wood pulp relies on shorter fibers that are often held together with acidic additives. Over time, these papers become brittle and yellow, crumbling away. Papyrus, however, possesses an inherent stability that our own archival paper struggles to match. The molecular bonds created by those ancient Egyptian artisans have proven more resilient than the empires that used them. Today, as we search for sustainable alternatives to our disposable paper products, the papyrus process offers a powerful blueprint. It shows us that the most durable materials can come from a clever rearrangement of natural structures, using a plant's own internal chemistry as the binding agent rather than synthetic adhesives. This ancient secret whispers a question to our modern world. What if we could design all our materials to be as intelligently integrated and as gracefully enduring as a sheet of papyrus? That same quest for a perfect, resilient surface found its ultimate expression not in a kiln, but in a living forest. Chinese artisans mastered a material that was essentially liquid wood, a sap that could be transformed into a coating of almost supernatural durability. This was Urushi lacquer, a substance harvested from the Toxicodendron vernicifluum tree, a process as perilous as it was precise. The raw sap itself is highly toxic, causing severe skin reactions akin to poison ivy, a danger the master lacquerers learned to navigate with careful skill. But the true magic began once the sap was collected. This was not a varnish that simply dried as the solvent evaporated. Urushi lacquer undergoes a fundamental chemical transformation, a complex reaction catalyzed by a special enzyme called lacquase. For this enzyme to work its magic, it requires a very specific environment, one of high humidity and a carefully controlled, cool temperature. The artisan was not just applying a finish, he was orchestrating a biochemical event. In the damp, humid air of a specially designed lacquer room, the enzyme activated, causing the urushiol molecules in the sap to begin linking together. They formed long, interlocking chains, cross-linking into a dense, three-dimensional polymer network. This process, known to modern science as enzyme-catalyzed oxidation, creates a molecular matrix of incredible stability. The result is a coating that is virtually impervious. It laughs at boiling water, shrugs off concentrated acids and alkalis, and remains completely unaffected by alcohol. Think of the most durable plastic coating you can imagine, and this ancient lacquer often surpasses it, all while being entirely derived from a natural, renewable resource. The application was a lesson in patience and perfection. A single object, like a ceremonial box or a piece of furniture, would receive dozens of impossibly thin layers. Each layer had to be applied with perfect evenness and then allowed to cure for days in its precisely controlled humid chamber before the next could be added. A single piece could take many months, sometimes over a year, to complete. This painstaking process built up a depth and resilience that a single thick coat could never achieve, creating a surface that was both mirror smooth and as tough as stone. Today, polymer scientists look upon Urushi with a sense of awe. It stands as one of humanity's first and most successful forays into controlled polymerization, a process we now use to create everything from nylon to Teflon. Yet our synthetic coatings often rely on petrochemicals and energy-intensive production. The ancient lacquer master, working with a toxic sap and a humid room, achieved a similar, and in some ways superior, result through a deep, intuitive partnership with organic chemistry. This secret offers a clear path forward, challenging us to look to nature's own chemical recipes for the next generation of high-performance, sustainable materials. Even the most brilliant Roman harbor would be useless if its foundations turned to mud. To build directly in the sea, their engineers needed a cement that could defy the water itself, a material that would set and harden into stone while fully submerged. This was the 20th secret, the magic of hydraulic cement. While our modern Portland cement paste simply dissolves and washes away in water, the Roman mixture did the exact opposite. It thrived in it. The key was a specific volcanic ash called pozzolana, named for the Italian town of Pozzuoli where it was first quarried. When this fine, reactive ash was mixed with slaked lime and then exposed to water, a powerful chemical reaction began. Instead of being diluted, the mixture underwent a process called a pozzolanic reaction, forming stable, interlocking crystals of calcium silicate hydrate. Think of it as the concrete growing its own skeleton underwater, a crystalline framework that binds everything together into a monolithic, water-resistant stone. Modern marine concrete fights a constant, losing battle against seawater, which slowly leaches out its binding compounds and introduces corrosive salts. The Roman concrete, however, used the seawater as a crucial ingredient in its own strengthening process. Recent research at MIT has revealed the true elegance of this ancient recipe. Using advanced microscopy, scientists saw that the specific combination of lime and pozzolana, with its precise particle size and mineral content, encourages the growth of these reinforcing crystals throughout the material's life. As tiny cracks inevitably form, seawater seeping in continues to fuel the pozzolanic reaction, filling the gaps with new, strong crystal growth. It is a material that possesses a built-in repair mechanism, growing denser and more resilient with each passing century. The Romans did not just invent a cement that could set underwater, they engineered a living stone, a material designed to evolve and improve within the very environment that destroys our modern equivalents. This ancient secret, now being decoded in our most advanced labs, holds the key to building the durable, sustainable coastal infrastructure of the future, from seawalls that fortify themselves to bridges whose foundations grow stronger with the tides. High in the thin air of the Himalayas, blacksmiths worked with metal that had fallen from the stars. Tibetan artisans held a profound reverence for meteoric iron, calling it sky metal and believing it carried the power of the heavens. This was not mere superstition. It was a recognition of a material with properties they found nowhere on Earth. The raw chunks of meteorite they gathered were composed of a unique nickel-iron alloy, a substance far different from the bog iron or ore smelted by other cultures. Its very origin demanded a new kind of craftsmanship, a specialized dialogue between hammer and anvil that had to account for the metal's peculiar soul. These smiths developed a suite of techniques specifically for this celestial material. They learned the precise temperatures at which to work it, the right rhythm of hammer blows, and the correct methods for annealing, all calibrated to manage a metal that could easily become brittle or develop flaws if treated like common iron. The spiritual power they attributed to their finished blades and ritual objects was made visible through a final, sacred step, etching the surface with mild acids. This revealed the otherworldly beauty locked within, the swirling, crystalline Widmanstetten patterns that are the signature of slow-cooled nickel iron in the vacuum of space. Modern science has since confirmed the sheer brilliance of their intuitive methods. Spectrographic analysis of these ancient Tibetan artifacts shows they often contain trace amounts of incredibly rare elements like iridium and gallium, metals that are vanishingly scarce in the Earth's crust but common in certain types of meteorites. These exotic elements would have drastically altered the metal's working properties, introducing challenges that could only be overcome through generations of patient, hands-on experimentation. A modern blacksmith, armed with all our metallurgical textbooks, would still struggle to forge such a material without causing it to fracture. The Tibetan masters, however, possessed a tactile knowledge, a feel for the sky metal that allowed them to coax it into forms of both deadly function and deep spiritual significance. Their work stands as a testament to a global truth that ancient genius often began with a simple act of looking up, recognizing a gift from the cosmos, and having the wisdom to learn its unique language. A master engraver's hand presses a fine chisel into a polished brass disc, tracing a curve of breathtaking geometric complexity. This was the creation of an Islamic astrolabe, an instrument where art and science merged into a single, functional masterpiece. Its face is a map of the cosmos, a web of lines and curves representing the celestial equator, the tropics, and the horizon, all engraved with a precision that seems to defy the limitations of the human hand. These artisans were not merely decorating metal, they were solving a profound engineering challenge using only their senses and generations of accumulated wisdom. The primary enemy was stress. The act of engraving itself, cutting deep lines into the brass, introduces internal tensions that can warp the entire disc, rendering its intricate scales useless. To combat this, the craftsmen developed a meticulous thermal ritual. They would anneal the brass disc repeatedly throughout the engraving process, heating it to a specific, dull red glow and then letting it cool slowly. This gentle heating relieved the locked-in stresses from the hammer and chisel, resetting the metal's crystalline structure and allowing it to remain perfectly flat. The sequence was everything, a carefully guarded secret of when to engrave and when to anneal, ensuring dimensional stability through thousands of precise cuts. The result was an instrument of staggering accuracy, capable of measuring angles down to fractions of a single degree. With such a device, a user could calculate the height of a minaret, determine the exact time for the 5 daily prayers based on the sun's position, or navigate the vast emptiness of the desert by the stars. This was a handheld computer built entirely from brass and intellect, its functionality entirely dependent on the flawless execution of its engraved scales. Today, engineers working in precision instrumentation look upon these astrolabes with a sense of awe. We achieve similar tolerances with computer-controlled laser etchers and air-conditioned clean rooms that eliminate thermal expansion. These ancient masters, working with fire, simple tools, and an intuitive grasp of metallurgy, rivaled the precision of early industrial machinery. Their work stands as a quiet monument to the power of focused skill, proving that the steadiest hand, guided by deep knowledge, can inscribe the heavens onto a disc of metal. West African sculptors faced a material rebellion every time they built a fire. The Nok culture's terracotta figures, with their intricate coils and dramatic features, were marvels of form, but their very complexity made them incredibly fragile. A head with a thick, solid crown and a delicate, hollow neck would expand and contract at different rates in the kiln, creating internal stresses that could shatter the entire piece in an instant. These artisans developed a firing control so sophisticated it was essentially a conversation with the clay itself. They orchestrated the kiln's temperature with a slow, patient rhythm, holding the heat at specific plateaus to allow the thicker sections to catch up thermally with the thinner ones. This prevented the violent steam pressure buildup that cracks most amateur pottery, but their genius did not stop there. They mastered the kiln's atmosphere, deliberately introducing wet green wood or other organic materials at a precise moment. This created a reducing environment, starving the fire of oxygen. In this smoky, oxygen-poor chamber, the iron oxides within the clay underwent a chemical transformation, emerging not as the typical red of oxidized terracotta, but in deep carbon-black grays and rich, smoky browns. This was not just for color, it fundamentally altered the ceramic body, making it denser and more resilient. The result of this total thermal command is a legacy that has survived 2,000 years of tropical humidity and temperature swings, conditions that would crumble modern, industrially fired clay. Today, studio potters and sculptors who create large-scale works look to the Nok for inspiration, trying to decode how these ancient masters achieved such structural integrity without a single digital thermometer or programmable kiln. Their secret was a holistic understanding of the entire process, from the clay pit to the last ember, treating the fire not as a brute force, but as a precise, responsive tool. A blade that could slice through the chainmail of its time was not forged in a common fire. The Viking Ulfberht sword stands as a metallurgical ghost, a weapon so advanced it seems to have fallen out of time itself. Modern analysis reveals its steel possessed a carbon content of around 1.5%, a level of purity and consistency that European blacksmiths would not achieve again for nearly 800 years. While their contemporaries worked with bloomery iron, a spongy mass filled with slag and impurities, the Ulfberht was born from a different process entirely, the crucible. This was a technology leap that should not have existed. The method was deceptively simple in concept, yet required a mastery of extreme heat. Raw iron and a carbon source, likely organic materials, were sealed inside a clay crucible and heated in a furnace until the entire contents melted into a liquid pool. This was the revolutionary step. In the bloomery process, iron never truly melts. It just becomes a soft, pasty mass that retains all its imperfections. But inside the sealed crucible, the molten iron could fully dissolve the carbon, creating a uniform alloy. The slag, being lighter, would float to the top to be skimmed off, leaving behind a pristine ingot of high-carbon steel. When this ingot was forged into a blade, the result was a sword of legendary performance. It was both harder and more flexible than any other weapon on the battlefield. It could be bent almost double and would spring back to true, its edge remaining lethally sharp through brutal combat. The distinct plus Ulfber plus T inscription stamped into the blade was not just a maker's mark, it was a brand of supreme quality, a guarantee of technological superiority. The origins of this secret, however, are shrouded in mystery. How did Viking smiths acquire such knowledge? The most compelling theory points to trade routes stretching all the way to Central Asia, where crucible steel was being produced in Persia and India. It is possible that Viking traders brought back not just finished ingots, but the knowledge of the process itself, adapting it in their northern homelands for a short, brilliant period. Another, more tantalizing possibility is that it was a localized European innovation, a flash of genius that was born, perfected, and then tragically lost, perhaps when a single master smith died without an heir to his knowledge. The Ulfberht secret vanished as suddenly as it appeared, and the quality of European steel regressed for centuries. This lost technology forces a humbling question. How many other peaks of human ingenuity have been scaled and then forgotten, leaving only their ghostly footprints in the archaeological record for us to wonder at? The final secret reveals a material born not from conquest or construction, but from a sacred game. Deep in the Mesoamerican ball courts, the Maya played a ritual that echoed through the jungle, its rhythm driven by the impossible bounce of a solid rubber ball. For centuries, how they created such a durable, elastic material remained a mystery, especially since modern vulcanization, the process of hardening rubber, was not patented until the 19th century. The Maya secret was a chemical recipe hidden in the rainforest itself. They harvested latex, the milky sap of the rubber tree, and then performed what seemed like a simple act of mixing. They combined this raw latex with the juice of the morning glory vine. To an outside observer, it looked like basic plant alchemy, but on a molecular level, a brilliant transformation was taking place. The morning glory juice contained sulfur compounds, the very same agent Charles Goodyear would later use in his famous vulcanization process. When the Maya stirred the two liquids together, the sulfur acted as a bridge builder. It created cross-links between the long, tangled polymer chains of the latex. Think of the raw rubber polymer as a pile of slippery, uncooked spaghetti noodles. They slide over each other easily, which is why raw latex is sticky and weak. The sulfur from the morning glory vine acts like tiny, stable staples, linking the noodles together into a cohesive, resilient web. This cross-linked network is what gives vulcanized rubber its strength and its ability to snap back to its original shape after being stretched or compressed. Laboratory recreations in recent years have confirmed the sheer effectiveness of this ancient method. The resulting rubber was not just bouncy, it was remarkably durable, able to withstand the immense impact of the ceremonial ball games without cracking or deforming. The Maya used this advanced material for more than just sports, crafting waterproof textiles, sturdy soles for sandals, and resilient containers. Their process achieved this stable rubber at room temperature, a stark contrast to the energy-intensive, high heat requirements of modern industrial vulcanization. This 25th secret completes our journey, bringing us full circle to a profound truth. These ancient craftsmen were not just lucky, they were the first polymer scientists, the original nanotechnologists, and the pioneering metallurgists. Their legacy, written in self-healing concrete, nanostructured steel, and vulcanized rubber, is a permanent challenge to our modern arrogance. It asks us to look beyond our digital screens and complex machinery, to remember that the deepest understanding of the material world often begins with observing nature's own quiet, brilliant recipes. That profound understanding of materials was not a permanent human possession. The brilliant secrets we have uncovered were often lost, sometimes for centuries, vanishing into the fog of history, not through a single cataclysm, but through a slow, silent unraveling of the very conditions that allowed such knowledge to exist. These techniques were not stored in digital clouds or public libraries. They lived and breathed within the minds and hands of a select few. The master artisan was a living library, and when that library closed, its contents often disappeared forever. Specialized knowledge was typically confined to tight family lineages or exclusive guilds, protected as a sacred trust and a source of economic power. This system, while ensuring quality and preserving trade secrets, was incredibly fragile. A single war, a plague sweeping through a city, or the death of a master without a worthy apprentice could sever a chain of transmission that had lasted for generations. The legendary formula for Greek fire died not because it was poorly made, but because the last family or guild that knew its precise composition was likely wiped out or scattered by the final sack of Constantinople. The loss was absolute. Furthermore, many of these advanced processes depended on a delicate globalism that we rarely attribute to the ancient world. The secret of Damascus steel relied on a specific type of iron ore from India, woots, traveling thousands of miles along established trade routes to the forges of Syria. When those routes collapsed due to political instability or the rise of new empires, the raw materials simply stopped arriving. Without the special ore, the smiths could no longer practice their art, and within a generation or two, the nuanced skills of thermal cycling and folding required to create the nanostructures were forgotten. The Industrial Revolution, for all its benefits, delivered the final blow to many surviving traditions. Its new philosophy valued speed, standardization, and scalability above all else. A process that took a master and several apprentices months to complete, like forging a single katana or applying dozens of layers of Urushi lacquer, had no place in a factory system designed for mass production. The subtle, sensory knowledge of reading the color of a flame or the sound of hammering metal was replaced by the consistent, but often cruder, control of a thermometer and a timer. We chose efficiency over excellence in many domains, discarding methods that produced superior results because they could not be easily scaled. This is why recovering these secrets is such a monumental task. It is not enough to simply analyze a piece of Roman concrete with an electron microscope. We must also become historical detectives, piecing together fragments from archaeology, trade records, and ancient texts to understand the economic, social, and environmental context that made such a material possible in the first place. The loss of this knowledge is a permanent cautionary tale, reminding us that technological progress is not a straight, ever-ascending line. It is a landscape of peaks and valleys, of brilliant summits achieved and then abandoned, waiting in the silence for us to find our way back.